Hi everyone, this is Mr. Hall and this is a quick video on rate of reaction calculations and interpreting rate graphs. The first thing I'm going to do is I'm just going to go through the basic equation of how you do these calculations. I'm not going to do calculation graphs yet, that'll be in another video because I want to also focus on just how you interpret the rate graphs in terms of how you do a written answer as to what's going on with them. So in terms of the objectives for today, it's to interpret rate of reaction graphs, and it's also to calculate the mean rate of reaction just from data that you've been given. So we'll start with the first one in terms of calculating this mean or average rate of reaction. So you need to know the rate equation, and there are two rates equations, although they're effectively the same thing. The first equation you have to know is that the rate of reaction is the mass of reactant used up or the mass of product that you make in grams divided by the time elapsed in seconds. The units for this is grams per second because basically you're measuring how much mass you've either gained as a product or how much mass you've lost as a reactant over time. So you always divide it by time. Now it doesn't have to just be in grams, it can also be the volume of a gas, and it tends to usually be the volume of a gas that you have produced rather than the volume that you've used up. So the second equation, which is virtually identical to the first, it's the mass of reactant used or product made in centimeter cubed divided by time. So you can see both equations are virtually the same. The only difference is the unit of the rate. In the first case it's grams per second, in the second one is centimeter cubed per second. There's a couple of things that you need to remember which I think is actually quite useful for the whole of science. First thing is, when you're determining rate, it's always a measure of how something changes over time. All right, so time is always going to be at the bottom of these equations. You're always dividing by time. And then the only difference between them really is grams and centimeter cubed. In questions, you're usually going to get the volume of gas produced. So you're usually going to be dealing with centimeter cubed per second, usually, sometimes per minute if they're being quite mean, but usually a centimeter cubed per second. Okay, so those are the equations that we're going to be using not only here, but in other videos when we're analyzing graphs. So let's have an example, just see how this works out. So let's have a look at this question. It says, in a reaction, 40 grams of a precipitate, solid, was made in 80 seconds. What is the rate of reaction and what would the unit be? So if we remember the equation from before that we just had in the previous slide, it's basically the amount of product. So I'm just going to put like mass of product. And that is always going to be divided by time. Now in this case, I have to look at the mass of product. I look at the question, I can see I've got 40 grams here. So at the top, I'm going to write 40 grams. And then this is happening in 80 seconds. That's my time. So I make 40 grams in 80 seconds. So I do 40 grams divided by 80 seconds, and that gives me 0.5 grams per second. So what that's telling me is that for every 1 second, I make half a gram. So if 80 seconds elapse, I make 40 grams, which kind of makes sense. So that's the mean or the average rate of reaction in this particular case. Let's take a second example. If I've got this reaction here, it says, in a reaction, 12.5 centimeter cubed of gas was produced in 5 seconds. What's the rate of reaction and what's the unit? So again, I have to write out my equation. So it's the amount of product or reactant, in this case it's product, and usually, to be honest, it's always product, and you divide that by time. All right, remember, time's always at the bottom. So I look at my amount of product, I look at the top here, it's 12.5. So I go back to here and I write 12.5. And that happens in 5 seconds. So I divide 12.5 divided by 5. Something which you might want to get into the habit of doing, and I find it really useful actually, I haven't been doing it so far, is writing the units here. So it's 12.5 centimeter cubed, and that is divided by 5 seconds. So if you do 12.5 divided by 5, that gives you 2.5. And you still got to work out what the unit is. Sometimes a question will give it to you if they're being quite generous. Sometimes they won't, and you have to kind of work it out for an extra mark. Actually, working out is really easy because you can see centimeter cubes at the top and seconds is at the bottom. So my unit here will be centimeter cubed per second. And the line there is because it's one divided by the other. Okay, so that's just two very straightforward examples of how you use this equation. And to be honest, you sometimes get questions like this where they give you the data like that. More often than not, you're going to be given a graph. Actually, if there's any question which is worth its weight in an exam, which is worth 10 marks or more, it's always going to be as a graph. I'm going to cover graph calculations later because they can be quite complicated. But the first thing I want to do is just work out how you interpret these graphs. Now, a typical graph will look a little bit like this, where you have time always on the x-axis over here, and then you've got volume of gas there. So what this basically tells you is how much of the product or reactant, whatever it may be, you are producing, if it's a product, over time. And you can see every rate curve you have will have the same shape, where it starts out kind of quite sharp, and then it will get kind of less steep over time until it eventually flattens out. So there's a couple of things you have to know about graphs like this. The first thing is, the steeper the line, the more product is made per second. And if you're making more product per second, it means you've got the highest rate, or your higher rate. So if we look at this particular graph I have here, you can see at the beginning the line is really steep in comparison to the rest. So that means that here the rate is very fast. Okay. But then, as you can see, as it goes on, it becomes less steep. I mean, at this point, it's far less steep than it was at the start. So here you would say that the rate is actually quite slow. It's got a low rate of reaction, if you want to use that kind of language. Second thing to mention is that the line becomes steep over time. I mentioned that, so the reaction's slowing down. And then finally, the reaction stops when the line is horizontal. So you can see at this point, this is when the line starts going horizontal. This is when the reaction stops. Okay. Couple other things. The total amount of product made in a reaction is the value reached when the line becomes horizontal. So if we look at this point, you can see the line becomes horizontal more or less. I'm just going to roughly sort of draw my line across. It's around at 42. I mean, I'd use a ruler if I was being a bit more precise, but it's around 42. So basically, in this reaction, you make 42 centimeter cubed of gas in total. That is your total product. A common mistake a lot of students do is that they try and add up the different data points, because they think, well, I made 25 here and I made 35 here, so I have to add the two together to get 60. That isn't how you do it, okay? All this does, it basically tracks how much you've made in total as the reaction goes along. So for example, between 3 seconds and 6 seconds, you've made another 10 centimeter cubed of gas. That's all it means. So don't get tempted to do the adding up thing. All you have to care about is where it finally ends up, and in this case, it's 42. So that's just the basic interpretation of how you look at these graphs. Now, when you're writing a full answer, you sometimes have to be given a 4 mark, and you have to describe and explain what's going on. Now, basically, all reactions have just basically 3 distinct phases. You've got stage 1, stage 2, and the stage 3 at the top there, which that top box is kind of cut out. So let's have a look at stage 1. So in stage 1, the reaction is very, very fast. Now, when you're writing an exam-style answer to a question, it's always quite good to quote data. So you'd probably say here, sort of between 0 and 3 seconds, the rate is fast. All right. And if you want to be really fancy, you can also calculate the rate, but we'll cover that later. You don't have to necessarily, you just have to say between 0 and 3 seconds, the rate is fast. Now, the reason why it's so fast at the beginning is because there's loads of reactant. Okay. Now, I'm going to cover the ideas around this later on collision theory, but for now, I'm just going to sort of just mention the basics, which is there's loads of reactant, so the frequency of collisions is high. Sorry, I'm just scribbling it there, but I'll go into more detail later on. So that's basically why. Now, in stage 2, you can see that the line's becoming less steep, which basically means that the reaction's slowing down. Again, using data here is really good. So you could say from 3 seconds onwards, the reaction slows down. Now, the reason why it slows down is actually really similar to the reasons given before. As the reaction proceeds, you're losing reactant, so you have less reactant than before. If you've got less reactant, it means you've got less particles which can react to form product, which means you get less collisions over time. The best way of writing that, instead of saying there are less collisions, say there's less reactant, so the frequency of collisions decreases. Okay? And then the final stage is the top one here, which is probably the most straightforward, is that the reaction stops. Again, you want to specify when that is. So we would say at 15 seconds, you can see it's all between 14 and 16, which is there. So you'd say at 15 seconds, the reaction stops, okay? And then the reason why it stops is because it runs out of reactant. So if you do the sort of describe and explain stage, or describe and explain sort of structure for each of your answers, you're likely to pick up all of the marks. They could be anything between 2 to 6, to be perfectly honest. Okay. Now, sometimes you'll be given the rate graph with a reactant. Don't panic if you see this. The only thing worth mentioning is that it's basically an inverse of what you saw before, where you started with a load of reactant gets used up over time, and the reactant's very fast because the line's very steep, but this time it's going down rather than up. And then over time it becomes less steep because you run out of reactant, so there's less collisions, and then finally the reaction stops when you run out of reactant. So here you've run out of reactant, and that's when the line goes horizontal. So you have a very similar pattern, but it's almost like a mirror image of what you saw previously. So don't get thrown by these kind of graphs. Just be aware that you can be represented the information differently. It's not common, but it can happen. Okay, so I hope that video was useful. The next one I'll do is be more about sort of details of how you do calculations from graphs themselves. Okay, best of luck with your calculations.